Hello and welcome. This is Let's Go to TimeTrack episode 6. In this video I will create an IPC messaging prototype. Here is an overview of how the messaging will work between two application instances, a master instance that is listening for a message and a secondary instance that is sending the message. The message is relayed through the shared memory, which we also used in the last episode to determine if the application is a single instance application. And there is another operating system feature that is used, which is a semaphore. And this provides a blocking function that is used to tell the master instance when a new message is ready to be read. So the process is as follows. The master instance starts up, and from the main thread it spins off a listener thread. The reason for this is that the semaphore acquire function is a blocking function, and the main thread or the main application for the main instance should show any message that is incoming. It should also stay interactive and not lock up the UI. So I put the locking part into a separate thread, and this can wait there until a message arrives and then wake up. Now there comes a secondary instance which wants to send a message to the main instance. So it writes the message to the shared memory. Then it releases the semaphore, telling the main instance, hey, there is a message waiting. The locking function call is released, and the main instance knows there is a message waiting, so it reads the message. And then the thread forwards the message to the main thread. So the listener thread says, main thread, here is a new message with a cute signal. And then it continues to wait for the next message. Now this prototype will have one application only. The master instance and the secondary instance will be the same application. And before this communication happens, the master instance will create the single instance application. And the secondary instance will just know, oh, there is a master instance, so I have to quit. But before it quits, it will check if it has a message on the command line. And when it was started with a message, then it will first send a message to the main instance and then quit immediately. So it goes away after the message is sent, and the main instance stays there. The reason for this is that when the main instance is already running, the time tracking is there and it's switched off. And I map a hotkey to the application command line with the message toggle, or the command line argument toggle. Then the application is executed, it sends the message to the master instance, the tracking status of the master instance is toggled, and the secondary instance quits immediately. So it's a dual purpose program combining the prototype from the last unit or the last episode and this episode. Now the communication process is not only used for communication between different instances, but also within an application. And the reason for this is that the listener is waiting in a blocked state. And when an application wishes to exit, for example, when a user clicks the close button on the window, it has to tell the thread to cleanly shut down. And while the thread is blocking, it is not handling any signals. So in the main thread could only send a terminate signal, which would be very unelegant, and the documentation says don't do that, it is a bad thing. It can leave your data in a corrupted state, it will leave your semaphore wherever it was, and it's just ugly. So instead we can just send a message, the next message from the main thread to the shared memory, same as if an external application would do it. Then release the semaphore from the main thread, which would unblock the listener, the listener then reads the message and says, oh, there is an exit message. That means I have to go away. The application is closing. Now this message could also come from another instance, another application. So it forwards the message to the main instance or the main thread before, just in case it doesn't know that an exit is imminent. Then it closes itself, and the main thread also says, okay, the listener thread has returned, so I close myself too. And the third scenario is really the same as the second one, just in this case an external instance, a secondary instance, sends the exit message, releases the semaphore, the signal unblocks, the message is read. Now it is forwarded to the main thread, which until now doesn't know that an exit is imminent, so the listener thread closes and the main thread knows, oh, there is an exit and I didn't instantiate it or start it, so I should shut down now because probably an external application did that. And the application shuts down. Preparation. Now I have created a barebone project with a lot of boilerplate. It has a main window class, which is inheriting queue label. It has an IPC message class, which is the class that handles the listening, sending messages, and determining if it's a master instance. It has a Boolean value to determine if a shutdown is already started from the main instance, and it has a slot for processing incoming messages and some boilerplate. So the application shows waiting for messages as a label and has an IPC message instance created. Now IPC message also has a lot of boilerplate. It is a constructor or destructor. It has a function or method called master status, which is the same as in the last episode, and determines if it's the master instance or a secondary instance. It has a function called, or a method called send message, and this class is inheriting queueThread, but these two functions are still executed in the main thread, so it belongs to the main thread, and only the logic that is in the run function is executed in a spin-off thread. So only the listener will be in a separate thread, and the other two functions here are in the main thread. Send message simply sends a message to the master instance, and this could be the same instance that is sending the message. There is a signal called incoming message, which is emitted each time a message is incoming with the message string, and a master shared memory, which is used to determine if this is the master instance and to read messages from. There is some boilerplate for all of these functions. Everything is empty so far. The master shared memory instance is created with TimeTrack shared memory string, and it is also deleted on exit. When I run the application, it shows an empty window with a message it's not empty. It shows a message waiting for message, but so far it doesn't do anything practically useful. So the first function or the first method I will implement is the run method. And this is the method that is spun off into the separate thread, and that is listening for release of semaphore and messages. So the assumption is that this listener is only created in master instances. Secondary instances will never create a thread, because they won't stick around long enough to get messages, and they don't have reason to get messages. They only send messages. So I have created the SHM master instance. And now I create the semaphore. with the string TimeTrack or key TimeTrack semaphore. Initial value is 0 and the mode is queue system semaphore create. Now this mode resets the semaphore, so if any other application before left the semaphore in an ugly state, or if it's in some other state than 0, it will be reset. And then I create an infinite loop. And this infinite loop processes messages as they arrive. So first it has a blocking call to the semaphore. And it waits precisely at this place until a message arrives. And when a message arrives, it will read this message from the shared memory. I come to this in a moment. Then it will emit the message, so the message will be qstring SG, and it will emit the message. It will check if the messages exit. And if the messages exit, then it means it's time to go. So it breaks the infinite loop, the while loop. And otherwise it recurses. And when it is going out of the loop, it will also delete the semaphore, so it won't bother anymore. So it's cleaned up cleanly. Run this application. Still doesn't do anything useful. Now, reading message from a shared memory is a little bit of very low level kung fu. The shared memory is basically a byte array in the memory with a given size, and I am deserializing this byte array to a qstring class, which is much easier to handle. So const char from equals char const pointer shm master data. I get a read-only pointer to the shared memory. I declare the message, and I also declare a text string stream, which is attached to the message. And then I read the message from the shared memory 1 byte at a time until there is a null terminator. So I read the byte into the stream and increment the from pointer and we run this application. It compiles. Now this isn't code anywhere so far, so this is just the preparation for this. Let's add some comments. Now the counterpart to this is the IPC send message. The IPC send message is called from the main thread instead of the listener thread. So this is in the main application, and it is a little bit tricky because technically it is declared in the queue thread derived class, but anything that is not in the run method is called from the parent thread. So the send message is also called from the parent thread, and I put it here because it is part of the whole messaging system, and it's a good place to keep it together. So here I create a new shared memory pointer. And I attach to it. Now one thing I forgot here was to create the shared memory master. And here I created, because this is the master instance, and to not get into conflict with the pointer of the master shared memory, I declare a new shared memory here, which is then deleted when the function or the method exits. So I attach to the shared memory as a client, or as a secondary instance, or as a message sender, and I lock the shared memory. And I unlock it, and I send the message. I unlock it, I create a semaphore, and I create a semaphore as open, meaning I attach to the existing semaphore that the listener is already listening, which is the same key, TimeTrack sem 0, and this time it's system queue system semaphore open. So any existing counters are left alone, and the master semaphore is also mostly left alone right now. At the end I also delete the semaphore, and in between I release it. With this release statement I unblock the listener of the master instance, which knows there is a message waiting. Yeah. So now I do the inverse of the message deserialization. Now I serialize the message, and for this so this is the message that is sent in the argument. I first get a pointer to the shared memory, and I get a pointer to the data of the string. And finally, I write the data to the shared memory. And part of writing to the memory is to setting the last byte to 0. So that the listener knows when the where the message terminates. The third method in the IPC message class is the master status, and this essentially does the very same thing as the last episode did. It determines if there is a master, this is the master instance or a secondary instance. So the assumption is that this is called before the listener is started. And this is the same thing as the last episode. It also uses the same shared memory as the master here. Because when I create the memory, and I'm a master, it's successful, I want to hold on to it. So use the same shared memory master in the listener that was used to determine if it's the master instance. So I move the ashire master create statement to the master status, and then I check what if the creation worked. So no. So I check the reason. That the creation failed. And if the reason is there is already an instance running, then I return false, meaning this is not the master. And as there is some kind of system issue, so panic, and otherwise, so if you didn't return here and didn't panicked, then I want to return true. This is the master. I run this application, so far it compiles. Now I have to glue all this together in the master instance. So the master instance, the main window, constructor will first check if it is the master. And if it determines yes, it is the master, then it will connect the IPC message signal to its own slot. And then it will start the listener thread. And then it will show the main window, which will display any incoming messages and wait for messages. So it will also interact with the user. The user can still close the window will stay responsive, and the listener thread will just stand by and wait for any message that it will forward to the master, to the main thread. Now, if it is not a master, then it is a secondary instance. Then it will check it if it has any arguments on the command line. And if there is an argument on a command line, then it sends the message to the master. And after this, it exits in any case. So it's still a single instance application. The secondary instance never sticks around, never shows the main window, it just exits. But it eventually sends an argument if it has any on a command line to the master instance to communicate with it. So the constructor will first check the master status. On startup. And if it is not master, then it will check if there is any argument on the command line passed. It checks if the size is bigger than 1. The first argument is always the name of the executable, and the second argument is, or the second value in the args array is the first argument. I just will care about the first argument here. If the user specified many more arguments, I don't care. If there is an argument, I will send this to the master instance. So and in any case, it should exit after it sent any eventual messages and it determines that this is not a master. Now this is the end of any secondary instance. Anything that comes below this belongs to the master instance. And the master instance will connect the incoming messages from IPC message incoming message. So any signal that is emitted is connected with this class's is incoming slot that I declared in the boilerplate. So main window is incoming. So any message that is incoming will trigger the slot. And finally, I start the listener with IPC and the exec method of the queueThread class that triggers a new thread, which is then spun off from the run method. So the listener will basically just start. Now what happens when a message is received? The listener receives a message, it emits the incoming message signal, this one, and this is connected to the is incoming or on incoming. Let's rename this. Rename is incoming, on incoming. So to this on incoming slot. And the on incoming slot will check if the message is exit. So a secondary instance can tell the main instance terminate now, but it also can come from the main instance. So first it will check if there is already a shutdown initialized. If the main thread already started a shutdown sequence, then it will change this shutdown started to true. So if msg is equal to exit, and shutdown started equals false. So if there is no shutdown imminent or currently ongoing, then we know, okay, an external application created a shutdown, so we close the application. Q application quit. And this will cleanly shut down the application. And if the message is not exit but any other message, then we just simply set the text of the application label to MSG, to the incoming message. And the distractor is the final piece that is basically just cleaning up, and this means that it is sending the exit message if it is not triggered by itself. So it registers the window is being closed, probably by the user who clicked the window close button. So it first checks if there is a shutdown already running. So to avoid an infinite shutdown loop, because external applications can also send a shutdown signal, I will first check if there is a shutdown already running. And then I send the exit message to the listener. And wait for it to finish. Now I run the application and I get an error message. Yep, wrong function call. It's not exec, it's start. Q application. Did I? core application. Okay, so this is the main instance. It now starts up and waits for the message. Now I go into the project configuration, the run configuration, and specify a command line argument. So this argument is foobar, any message. And then I run a secondary instance. And the secondary instance started up. It recognized, oh, I'm the secondary instance. And it recognized, oh, there is a command line argument foobar. So it sent the message to the main instance, which is still this one. And then it immediately exited with successful exit code. You can also run it with a different message. For example, toggle. So I can send multiple messages. These will recurse. And I also can send the exit message, which will terminate the main application. I can also obviously just start the main instance and then close it, which will then cleanly shut off. So when I start the next main instance, it works nicely again. And when I send in the next instance, the secondary instance, it sends the message. So this concludes this prototype. This is one of the more complicated prototypes because it uses such low-level system primitives. But it is a very elegant way to talk between application instances. And using the queued queue system, semaphore, and queue shared memory, this is also a quite portable way. So this runs on all the major desktops and works as expected. Thanks for tuning in, and goodbye.